If I remember correctly, it's the one where if two angles are subtended by the same chord or chords that are the same length, then the two angles are equal to each other. Is that correct? Or is it the one where an angle at the center of a circle is double the angle at the circumference? I think it's the one, I think it's this one. The other thing is, fortunately, with theorems of Euclidean geometry, you don't necessarily need to know which one is 1, 2, or 3, or whatever. All you need to know is what the theorems say. You get it? Not like their number, because the number is better. So let's just say theorem 2. Here, right? Theorem 2. So theorem 2, it could be mixed up with 3, but let's just write a theorem here. Theorem 2 states that if two angles, all right, are subtended by the same chord, then those two angles are equal to each other. You see? So subtended, it almost like visualize a picture where you almost like have a string. Imagine this is like one string here, here, and there. That's like, imagine you have like one string like this. If you're gonna pull it here, right, it's going to make a shape like that. Do you agree?
Yeah.
Yeah. So that's what subtended basically means. You can have a circle here and a circle there. You see, this could start off like this, and then if you pull this going upwards, you'll have something like this. You get it? Yeah. So that's what the word subtended means. It just means that the two sides, or rather the 2 points of the 2 points that are like holding your angle, those are the 2 points where those are the 2 points that are like subtending your angle. It's a weird word. So for example, if this is angle A, right, and this is angle B, and this is angle C and D, angle A is subtended by the arc DC. See, angle B is also subtended by the arc BC. And we can go on and on and on. Angle D is subtended by the arc AB. Same as angle C. It's subtended by the arc AB. You see, that's like basic knowledge. You get it? So the moment maybe they have like a line here and a line there, that like adds more angles. You see, and now you can say it's subtended by the arc. I mean, you can say it's subtended by the chord DC. Like A is subtended by the chord DC, B is subtended by the chord DC. You see, and then here C is subtended by this chord AB, D is subtended by this chord AB. But it even gets worse now, because now you have more angles if we had those lines, because now this angle here is equal to that one, and those angles are subtended by the arc BC, or you can say subtended by the chord BC. Do you see that? Yeah, and the same goes for this one. This angle is equal to that one, because angle C, this angle here, which is called angle DCA, is subtended by the arc AD. Same as angle ABD here. This angle is subtended by the arc AD also. You see it? Yeah. You can also say it's subtended by the chord AD. Doesn't matter what you want to say, arc or chord. As long as the line is there, you can say chord. If the line is not there, you can say arc, because there'll always be an arc wherever there's a chord. Vice versa. Yeah. So, in simple words, right? Equal chords subtend equal angles. And then we can say here vice versa, because that's the thing, you want to remember with these laws. They work in reverse also, meaning if you see the angles, if you see the sides are equal to each other, if say you have I'll show it. When I say vice versa, I mean a scenario like this one, where the sketch may be a bit different. So the vice versa part, this is why. If I have a circle, right? And I have two chords that are at separate places in the circle. Let me just draw my circle properly here. If I have two chords that are at separate places, and those two chords are equal and they are both subtending angles. If I have a picture like that, let's show it. So say I have a chord over here. There's a chord here. And say I have another chord. Let me also make it, let me make it a different color. But let's put lines to show that they're equal. If this chord here is subtending this angle, right? Over here. And then I have this green chord here subtending another angle. Let's say this angle is like somewhere there, like this, like that. The moment you know that these chords are equal, as long as these chords are equal, it means that whatever this angle is, if it's A, if this one is B, they will be equal to each other, because the law says equal chords subtend equal angles. You get it? What I mean is, this picture, actually, let me put it the other way around. Let me leave the lines out. You see, because this one almost shows, this one is almost the first version, because the chord is definitely a sharing. They both share the same chord. So that one is visibly there. This one, if only the angles were told to be, if they told us that the angles were equal, which is what they would need to do, or show us, or whatever, or would have proven it, or whatever. If this angle, if they tell you that it's equal to this one, automatically these chords would be equal to each other. You see, what I'm trying to say is there's no scenario where these are equal and these chords not being equal. The chords don't have to be the exact same line. The length just has to be equal. You see? You see it? Yeah. So that's this theorem. You see, just look out for chords, and you have to look out for where angles go. That's the law. That's the trick with Euclidean geometry, actually. When you're going to be working with angles, say you're actually like looking for angles, trying to figure them out, and all that, right? The one thing you need to do is you need to trace where the lines go, meaning any angle has two lines that go somewhere, like angle A, this part that's green. The one line goes to D, the other line goes to C. So you also then want to look for another line that is going to, other lines that are going to D and C, that are also like coming from the circumference of a circle, and that's only coming from B. You see, directly from B here, you have a line going to D. Directly from B here, you have a line going to C. Now, the other thing is, with your Euclidean geometry, if say a specific spot is not like labeled with a letter, it's normally a point where you may not necessarily need to worry about it. You see, yeah. So that's for theorem 2. Are there any questions on theorem 2? Okay, so let's go to the third one. So the third one is very, okay, not that special. It's just a theorem. All these theorems, you don't want to put any of them on a pedestal. You actually just want to be friendly with all of them. You want to memorize all of them. You see, the thing is, the easier you can memorize these, the easier you can recall these theorems, right? The better. Like you will find yourself almost feeling like, I don't know, a lot of people are going to struggle with Euclidean geometry because they do not read the theorems until they have memorized them. You see, the moment you read the theorems and you memorize them and you're able to say, okay, what does, if you're able to look at a picture and say what the theorem says, you're fine. You see, you want to be able to say it and you want to be able to write it out. You see, so meaning if you see something like this in a sketch, in a book, wherever, you want to know, okay, it's that theorem. It says that two angles subtended by the same chord are equal. As long as you know that and you can say it easily, freely, and all that, you're fine. You see. So here, let's see here, theorem 3. This is what theorem 3 says. You see. Circle. Let's do theorem 3. So theorem 3 again works with the center of the circle. That's what theorem 3 does. It works with the center of the circle. So this is the idea. This is the center of the circle. Now this center of this circle, there's a lot that comes with the center of the circle. Firstly, the center of a circle, if you have an angle here, right, that's being formed at the center of the circle. Like there's a line going to the circumference. Wait, got to like chop this so that it's not too long.